Hello, everybody, and welcome to the new lecture. This lecture is the last one in chapter 1, and hopefully by today we'll finish all the materials for chapter 1. I will then start to give you some questions as a tutorial so that you are able to solve and apply the theory that we have taken. Anyway, so today's lecture is about analogies among molecular transfer phenomena. That is the title for today's lecture. We should be able to understand what's the meaning of analogies at the end of this lecture. So objectives, two objectives, very clear. The first one is to identify the analogies among molecular momentum, heat, and mass transfer for the simple case of a fluid flow past a flat plate. Second objective will be to define and interpret the following dimensionless numbers: Schmidt number, Prandtl number, and Lewis number. Then I will give you one example or one exercise to be done, and you should be feeling comfortable to do it. So, in the flow of a fluid past phase boundary, there will be velocity gradient within the fluid, which results in a transfer of momentum through it. In some cases, there is also a transfer of heat by virtue of a temperature gradient. So if we have fluid and it is passing a phase boundary means if we have, for example, gas and liquid, or we can have liquid and liquid. So if there is a kind of boundary between these phases, for the fluid which is past a phase boundary, which is a kind of boundary between the phases, there is a velocity gradient, change in velocity within the fluid itself. And this velocity gradient will result in transfer of momentum. So when you studied fluid mechanics, they spoke about the change in velocity, and they call that one momentum transfer. In some cases, there is also transfer by heat by virtue of temperature gradient. So if you have a temperature gradient, you will have heat transfer. If you have velocity gradient, you have momentum transfer. The process of momentum, heat, and mass transfer under these conditions are intimately related. So now, so far we have been taking mass transfer alone, but now we are telling you we cannot deal with it separately. Sometimes all of these transfer phenomena happen at the same time. So what are the transfer phenomena? Well, you know mass transfer is there. From heat transfer, you know there is a change in temperature causing heat transfer. And you also know from fluid mechanics that change in velocity will create for you momentum transfer. So if these are happening at the same time, can we relate them? That's the question. So can we consider the analogies among them? So can we relate them? Can we consider the analogies? But so far we don't understand the meaning of analogies. Okay. Let's proceed more. Consider velocity profile for the case of a fluid flowing past a stationary flat plate. So from fluid mechanics, you have taken fluid passing a flat plate. So if you look at the diagram in front of you, there is a fluid which is U0 and it is flowing past a flat plate. there is what? There will be velocity gradient. At the solid surface, we know that the velocity is zero, but then there is a kind of laminar boundary layer next to the surface of the flat plate, and it will increase. That's laminar boundary layer. We have taken it in the fluid mechanics. Within this region, the shearing stress required to maintain the velocity gradient was given to you. And we said at one stage in the fluid mechanics that the shear stress is proportional to the velocity gradient, which was the du over dz. Then, when you remove the proportionality and you put the equal sign, you put a constant. That constant, we called it its viscosity. So shear stress is equal to this minus viscosity multiplied by the velocity gradient. So that equation is already known to you. U is the fluid velocity, which is parallel to the surface, and Z is the it is measured as increasing toward the surface. This can be rewritten. Now we can rewrite it as shear stress is equal to viscosity divided by rho multiplied by derivative of U multiplied by rho divided by dz. How this happen? We just introduce the rho. So viscosity divided by rho, and we are assuming that this rho is constant. This is the reason it has gone into the derivative term. So then this equal to minus v multiplied by the derivative term. The v actually, it is the kinematic viscosity, which is this dynamic viscosity divided by rho. And this term is called momentum diffusivity. So from now on, the viscosity, dynamic viscosity divided by rho, we will call it momentum diffusivity. The kinematic viscosity has the same dimension as the mass diffusivity. Mass diffusivity, which we have taken it in the previous lecture, we said, for example, the unit is centimeters squared per second. So it is length squared per unit time. While the quantity U multiplied by rho can be interpreted, we can say it is equal to volumetric momentum concentration. So volumetric momentum concentration is basically U multiplied by rho. So what is inside the derivative here, U multiplied by rho, we call it the volumetric momentum concentration. And the shear stress may also be interpreted as viscous momentum flux. So it is equal to viscous momentum flux. So now we define each one of them as words rather than just symbols. Now we are introducing to you some dimensionless numbers. You know, one of the dimensionless numbers in the fluid mechanics was Reynolds number, for example. Reynolds number was the only dimensionless numbers we have taken so far. They will also introduce you some dimensionless numbers and heat transfer. But for me, I'm introducing now to you the Schmidt number. Schmidt number is a dimensionless number, which is basically a ratio of momentum and mass diffusivity. So if you look at the equation in front of you, Schmidt number is equal to viscosity, dynamic viscosity divided by rho, divided by mass diffusivity. So DAB, we call it mass diffusivity. And rho, viscosity divided by rho, we call it momentum diffusivity. So this ratio of momentum diffusivity divided by mass diffusivity is called Schmidt number. There is another number, it's called Prandtl number. Okay, Prandtl number is related with the heat transfer. So when a temperature gradient exists between the fluid and the plate, the flat plate that we have spoken about, the rate of heat transfer in the laminar region, we can say it is Q, which is the heat transfer, the Q, you know it, is proportional to the change in temperature. So if we remove the proportionality, it's equal to minus K. K is the thermal conductivity of the fluid itself, and multiply by the dT, change in temperature, divided by the dZ. So we can rewrite it also again, as we have done before. Q is equal to K minus K divided by Cp rho. So if we introduce the Cp rho, then you have to again multiply the derivative term by the same number. So it's multiplied by the derivative T inside of it is Tcp rho divided by Z. We can say now that this term K over Cp rho, we will say it is equal to alpha. So the Q is equal to minus alpha dt Cp rho divided by dz. Cp from heat transfer and thermodynamics is the specific heat at constant constant pressure. The quantity Tcp rho may be looked upon as the volumetric thermal concentration. So as we have done also a similar approach, we named these variables. So Cp is specific heat, and the Tcp rho, we can call it as volumetric thermal concentration. And the alpha is basically K divided by Cp rho, is the thermal diffusivity. So we have the mass diffusivity now, we have the momentum diffusivity, and we have the mass thermal diffusivity, which is the alpha. If you check the units, basically the units also of this diffusivity term will be length square per unit time. So Prandtl number is defined as a dimensionless ratio of momentum and thermal diffusivity. So the momentum diffusivity was what basically? It was viscosity divided by the density, if you remember, and thermal diffusivity was Cp divided by K rho. So now actually what I want you to do, put these terms together in this equation and see how the density will be crossed. Okay, so the definition of Prandtl number is momentum diffusivity over thermal diffusivity, and then put the definition for each one of them and try to prove that Prandtl number is Cp viscosity over K. Lewis number. This is our final number, which is the Lewis number. Lewis number is basically a ratio of thermal and mass diffusivity. So if you take thermal diffusivity and you divide it by mass diffusivity is basically simply diffusivity AB, DAB. So that's your mass diffusion. So if you put the thermal diffusivity and divide it by mass diffusivity, you can now prove that this is equal to Schmidt number divided by Prandtl number. So there is a relationship now between Schmidt and Prandtl number, and this relationship is given to you by the Lewis number. So now the Lewis number is basically combine two things together, the heat and mass transfer. So before, the Prandtl number was for the mass diffusivity, and the Prandtl number was basically for the heat transfer, and the Schmidt number was for the mass transfer. Now, you have both of these transfers combined in one relationship. So that's the beauty of it. So Lewis number is combining mass and heat transfer together. Examples of these kind of operations is humidification operation. You have taken possibly this in thermodynamics, humidification operation. So you have the water vapor, which will be humidified. So there is a kind of mass transfer because there is evaporation, and you have the condensation also happening. So this kind of transfer, there is mass transfer, and there is also change in temperature. So there is heat transfer. So it is combined nicely and Lewis number. So an elementary consideration of the process of momentum, heat, and mass transfer leads to the conclusion that in certain simplified situation, there is a direct analogy between them. There is a direct relationship between them. So you can not only take a look at them separately, you can combine these two transfers or even three transfers together. Momentum transfer together, heat transfer together, and mass transfer together. So, and this is what's happening. So let's take an example and try to apply that. It has been observed that for system air water vapor at a near ambient condition, the Lewis number is equal to 1. So your system is air, binary, air and water vapor, and the Lewis number for this case was proven to be 1. This observation called Lewis relation, which has profound amplification. It's important for the humidification operation. Based on this Lewis relationship, that Lewis is equal to 1, estimate the diffusivity of water vapor and air at 300 Kelvin, 1 atmosphere. So he wants you to find the diffusivity of water vapor and air, DAB. After that, you compare your results with the value predicted by Wilkie-Lee equation. So I have given you the Wilkie-Lee relationship. You have to go back now, calculate the diffusivity for this case using the Wilkie-Lee equation, and compare the value that you get from Wilkie-Lee equation with the value that you will get from this Lewis relationship. So I have given you also all of the physical properties. So for air at 300 Kelvin and 1 atmosphere, all of these physical properties like Cp, specific heat, thermal conductivity, viscosity, and rho for air at the temperature and pressure of 1 atmosphere is all given to you. As you can see also, the density of air is around 1, so 1.18 kilogram per meter cube. And the viscosity is constant multiplied 10 to the power minus 5. So it's quite low. So you can see and feel the values of the physical properties. You should be able to do it. And I'm expecting the answer to be almost similar. You can prove this yourself. And after we finish this theory, as I said, next lecture, I'll bring you some questions we'll try to solve. Please put the answer, anybody who do it, I want him not to put it on WhatsApp. I want him to put the answer in the Microsoft Teams so that it is a kind of record for us. Have a good day and enjoy this calculation.